Good day and welcome to One-on-One Maths Private Tutors. Today we are going to look at IGCSE and O-Level Physics for Cambridge and ZIMSEC. In this section, we are looking at the reflection and the refraction of light waves. Sources of light. You can see an object only if light from it enters your eyes. Some objects, such as the sun, electric lamps, and candles, make their own light. We call these luminous sources. Most things we see do not make their own light, but reflect it from a luminous source. They are called non-luminous objects. So we can see in this diagram we have our luminous source being the light bulb, and our non-luminous sources being the table, the chair, the books, the shelf, and even the woman there. Luminous sources radiate light when their atoms become excited as a result of receiving energy. In a light bulb, the energy comes from electricity. The excited atoms give off their light haphazardly or in all directions. Rays and beams, sunbeams streaming through trees, and light from a cinema projector on its way to the screen both suggest that light travels in straight lines. The beams are visible because dust particles in the air reflect light into our eyes. The direction of the path in which light is traveling is called a ray and is represented in diagrams by a straight line with an arrow on it. A beam is a stream of light and is shown by a number of rays. So these are beams of light. In the first case, the rays are parallel. In the second case, the rays are diverging. In the third case, the rays are converging, which means they are coming to a point. So in our study, we will use rays to represent light, speed of light. Proof that light travels very much faster than sound is provided by a thunderstorm. The flash of light is seen before the thunder is heard. The length of time lapse is greater the further the observer is from the storm. The speed of light has a definite value. Light does not travel instantaneously from one point to another, but takes a certain very small time. Its speed is about 1 million times greater than that of sound. The speed of light through open space or a vacuum is 3 times 10 to the power 8 meters per second. Reflection of light. Reflection is bouncing off of waves from a surface. A mirror can be used to change the direction in which light is traveling. An ordinary mirror is made by depositing a thin layer of silver on one side of a piece of glass and protecting it with paint. The silver at the back of the glass acts as a reflecting surface. A plane mirror is produced when the reflecting surface is flat. Law of reflection. The terms used in connection with reflection are shown here. The normal line. The normal is the line which is perpendicular to a surface. So if we have our mirror there, we can have the normal being the perpendicular line, which means this is 90 degrees to the surface of the mirror. The angle of incidence is the angle between the incident ray or the incoming ray and the normal. So if our ray of light is coming onto the mirror like that, we say this ray is incident onto the mirror. So this is our incident ray, and the angle of incidence is the angle between the incident ray and the normal to the surface. So this is the normal, this is the incident ray. So this is our angle of incidence, which we give the symbol I. Angle of reflection is the angle between the reflected ray and the normal to the surface. So if we are saying our ray is reflected, which means it bounces off this plane mirror surface, then it will bounce off like that. and we call it the reflected ray. The angle between the normal and the reflected ray is our angle of reflection, which we give the symbol R. So usually we represent our plane mirror like that. So this is another diagram showing it. Now, the law of reflection states that the angle of incidence is equal to the angle of reflection. That is the law of reflection. States that angle of incidence I is equal to angle of reflection R. Let's look at this practical we can do to prove the law of reflection. And this experiment should be carried out in a dark room. So what you'll need is a lamp that is shielded so that a beam of light comes through an opening, and then a single slit that should further narrow down the beam into a thin, straight beam. Then we need a sheet of paper and a plane mirror, which is a flat mirror. Draw a line A or B on a sheet of paper and using a protractor mark angles on it. Measure them from the perpendicular ON. So first you must have your sheet of paper with a line AB and on the center mark O. Then construct the normal, which is a perpendicular line using a protractor at the center O. Then start marking angles from the normal using a protractor. Mark out 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, 80 degrees, and so forth on the paper. Set up a flat or plane mirror with its reflecting side on A or B. So now you put your mirror there with this side as the reflecting side, so that when light is incident on this mirror, it will be reflected there. Shine a narrow ray of light along, say, the 30-degree line onto the mirror. So now you make sure that your lamp and your single slit is set up that light will be incident on the plane mirror at, let's say, 30 degrees. Then mark the position of the reflected ray. So we're supposed to have a ray reflected there from the mirror at the point at which it is incident. So now we can mark this position by putting two dots along the reflected ray. Remove the mirror and measure the angle between the reflected ray and the normal. So we have to measure this angle there. Repeat for other angles of incidence. So you have to change your angle of incidence now, let's say 45 degrees, and see how much that ray is reflected, and then measure the angle of that reflected ray from the normal. So after this experiment, we should be able to prove the law of reflection, which says the angle of incidence is equal to the angle of reflection. If the angle is incident at 30 degrees from the normal, our reflected ray will also be 30 degrees from the normal. So we can use this law of reflection in periscopes. A simple periscope consists of a tube containing two plane mirrors fixed parallel to and facing each other. Each makes an angle of 45 degrees with the line joining them. Light from the object is turned through 90 degrees at each reflection, and an observer is able to see over a crowd. This is a periscope. We have a plane mirror there at 45 degrees to the line joining them. So this angle is 45 degrees, this angle is 45 degrees. This angle is 45 degrees, and this is the normal. You can see over obstacles, such as this wall. The light from an object on this side will be reflected through 90 degrees, and you will be able to see it. So this is a periscope in action. Two plane mirrors inside there. These people can see over a crowd. Now let's look at regular and diffuse reflection. If a parallel beam of light falls on a plane mirror, it is reflected as a parallel beam of light, and regular reflection occurs. So this is an example of regular reflection, a parallel beam of light coming in, being reflected as a parallel beam of light. Most surfaces, however, reflect light irregularly, and the rays in an incident parallel beam are reflected in many directions. This is known as diffuse reflection. So if the surface is rough or not flat, then the rays in a parallel beam of light will be reflected in all directions. In everyday life, we see this in bathroom windows. Because they are rough, when light falls on them, it is reflected in a haphazard manner so that a person who is outside the bathroom cannot get a clear view of the inside of the bathroom. This is because light is reflected in a diffuse pattern which distorts the image inside the bathroom. When you look into a plane mirror on the wall of a room, you see an image of the room behind the mirror. It is as if there were another room. Restaurants sometimes have a large mirror on one wall just to make them look larger. You may be able to say how much larger after the next experiment. The position of the image formed by a mirror depends on the position of the object. In this experiment, we will use plain glass to show reflection. Bear in mind, this is not a mirror, this is a piece of glass. So we support a piece of thin glass on the bench. The bench has a dark surface. The glass must be vertical, which means the angle between the glass and the dark surface should be 90 degrees. Place a small paper arrow, so we take a small white paper arrow about 10 centimeters from the glass. So the distance should be about 10 centimeters from the glass. The glass acts as a poor mirror, and an image of O, which is this white paper arrow, will be seen in it. The darker the bench top, the brighter the image will be. So we should see an image of this white paper on the plain glass. Lay another identical arrow I on the bench behind the glass. So we should place this arrow behind the glass, move it until it coincides with the image of O. So the observer on this side should see on the glass this paper directly on the image of this white paper here. So this is moved until it is on top of the image they see through the glass of this. How do the size of O and its image compare? Now, since O and I are identical, if I is placed directly on the image of O in the mirror, the image in the mirror should be the same size as I, which is also the same size as O. So there should be a straight line joining O and the image of O with I directly on top of the image of O in the glass. Measure the distance of the points of O and I from the glass along the line joining them. How do these distances compare? So if we have our plane mirror there, our O, if this is 10 centimeters and say this is 11 centimeters and the distance there is 12 centimeters. If we measure I there, the point on I, which is this point, from the mirror, it should be the same distance. This point that is corresponding to that point should also be 11 centimeters. This point, which is corresponding to that point, should be the same distance, which is 10 centimeters in this case, and this point, which is corresponding to this point, should be 12 centimeters from the mirror. So this experiment proves that the image is the same distance from the mirror as the object. If this is the object O and this is the image I, then they are placed the same distance in front of the mirror as behind the mirror. Real and virtual images. A real image is one which can be produced on a screen and is formed by rays that actually pass through the screen. A virtual image cannot be formed on a screen. The virtual image is produced by rays which seem to come from it but do not pass through it. The image in a plane mirror is virtual. Rays from a point on an object are reflected at the mirror and appear to our eyes to come from a point behind the mirror where the rays would intersect when extrapolated backwards. So, real images are formed by rays actually coming together to form an image. Virtual images are formed by reflected rays that appear to our eyes to come from a point behind the mirror where the rays would otherwise intersect when pushed back. Now, this is an illustration of how virtual images are formed. If we have an object there, rays of light would come onto the mirror. An observer on this side, these rays bounce off the mirror. And since these waves are diverging and not converging, an image is not formed from these rays. And the image is extrapolated from virtual rays or pulled back, and the image we see does not come from the rays themselves, which are reflected, but from these virtual rays, which are extrapolated or pulled back to a point where they seem to originate. And it should be noted that a real image is formed when real rays converge. A virtual image is formed when virtual rays converge. When rays diverge, an image is not formed. Okay, these rays are virtual, which means they are not real rays. The real rays are these ones that are incident and are reflected. Lateral inversion. If you're standing on a mirror and you close your left eye, your image in the plane mirror seems to close the right eye. In a mirror image, left and right are interchanged, and the image appears to be laterally inverted or inverted sideways. Left becomes right and right becomes left. The effect occurs whenever an image is formed by one reflection and is very evident if something printed is viewed in a mirror. So, these are the properties of an image in a plane mirror. First, it is far behind the mirror as the object. So the distance, if we have an object being viewed through a plane mirror, the distance between the object and the mirror is the same as the distance between the mirror and the image. The object is the same size as the image. Size does not change. And the image is virtual, which means it originates from the extrapolation or pulling back of the rays to a point where they seem to originate. Now let's look at this question. Fig 7.1 shows two rays of light from a point O on an object. The rays are incident on the plane mirror. So this is our plane mirror. This is the point on an object. These are the two rays incident on the plane mirror. On Fig 7.1, continue the path of the two rays after they reach the mirror. Hence, locate the image of the object or label the image I. So what do we need here? We need a protractor so that we can construct the normal from the plane mirror. So our normal is a 90-degree line from the point of incidence on the mirror. So this is the position of our normal for this point of incidence. So now we can connect our normal there. Then we also create a normal there for this ray. So these are our two normals there. Now, from the law of reflection, angle of incidence should be equal to the angle of reflection. Our angle of incidence here is 50 degrees for this ray. So we can see this is 50 degrees there. So our angle of reflection should be 50 degrees also. So here is 50 degrees there. Then we connect there our reflected ray. So this is being reflected, which means it's bouncing off. So this is 50 degrees. Now let's look at the other ray. The angle of incidence is 60 degrees. Yeah. So the angle of reflection should also be 60 degrees, which is here 10, 20, 30, 40, 50, 60 degrees. We join this to the 60 degree. Now that is our reflection of this ray. If this is 60 degrees, then this is 60 degrees. Now, these rays are not meeting up to form an image there. They are diverging. So, in order to get an image, we have to extrapolate them, which is to pull them back to a point where they would meet. So, we extend them back like that, then they will form an image over there. So this point where these lines are pulled back, which we can now call the position of our image. That's why we call it a virtual image, because it's not formed from the meeting of the rays, but an extrapolation or the pulling back of the rays to where they would otherwise meet. And this distance here from the object to the mirror is the same as this distance here from the mirror to the image. So that's how an observer, let's say someone who is there looking, will see an image on the mirror of something that is there. So we have continued the path of the two rays after they reach the mirror by reflecting them, and we have located the image of the object by pulling back these rays using virtual rays. These are real rays, and these ones are virtual. Now, to describe the nature of the image, we'll say it is virtual, same size as the object, and it's laterally inverted. So this is the description of an image on a mirror. It is formed by virtual lines, so it is a virtual image. It is the same size as the object, and it is laterally inverted, which means left becomes right and right becomes left. So that is the construction we have to do for objects and images on a plane mirror. Now let's move to refraction of light. Although light travels in straight lines in a transparent material such as air, if it passes into a different material such as water or glass, it changes direction. At the boundary between the two, it is bent. The bending of light when it passes from one material or medium to another is called refraction. Terms used in connection with refraction are shown in the table below. The angle of incidence, I, is the angle between the incident or incoming ray and the normal. Similarly, the angle of refraction, R, is the angle between the refracted ray and the normal. So if we have two mediums, say from air to glass, we can say glass is optically denser and air is less optically dense, which means it is easier for light to travel in air than in glass. So if we have an incident ray of light coming in from air, to glass. And we have our normal there, which is perpendicular to the surface of incidence. Then this is our angle of incidence I between the normal and the incident ray. Now, when light enters from a less optically dense medium to a more optically dense medium, it is bended towards the normal. So this is our angle of refraction, and our wave continues to move inside the optically denser medium. When the wave leaves the optically denser medium at the other end, it will resume its original direction with which it enters. So this ray will be parallel to that ray. And as it leaves there, it is bended away from the normal with the same angle I. And using the idea of parallel lines, we can say this is the same as R. Because this is the same, this angle here is the same as that angle here. So the angle of refraction is the angle between the refracted ray, this ray which has been refracted or bended, and the normal to the surface. This is the normal to the surface. Facts about refraction. A ray of light is bent towards the normal when it enters an optically denser medium at an angle. So we can see A is less optically dense, glass is more optically dense, so this ray is bended towards the normal. So we can say I, angle of incidence, is greater than angle of refraction. So the angle of refraction R is smaller than the angle of incidence. 2. A ray of light is bent away from the normal when it enters an optically less dense medium. For example, glass to air. So we can see here from glass to air, the ray is bended away from the normal. So we can see here, this angle is less than that angle. A ray emerging from a parallel-sided block is parallel to the ray entering, but is displaced sideways. So we are saying this ray emerging from a parallel side block, if these sides are parallel, this angle is the same as the one entering. So this angle is the same as that angle. But it is displaced sideways, which means this bending has caused it to emerge at that point and not at that point. If this incident ray was not refracted here, it would emerge at that point. But since it was refracted, it would emerge at this point and not that. So that is what we mean by displaced sideways. A ray traveling along the normal direction at a boundary is not refracted. What do we mean by that? If we have our glass block and this is our air, this is our glass, and we have our normal there, if our wave is traveling parallel to the normal, which means in the same line as the normal, into glass, it is not bended. It will go straight through. So if our ray is traveling perpendicular to the surface, to go straight through. So those are facts about refraction. Let's look at an experiment to demonstrate refraction in glass. So again, this experiment has to be done in a dark room. So this is the setup we should have. Again, a single slit, a shielded lamp on a lampstand, a beam of light coming through, and a single slit to narrow it down into a straight ray. We set up our glass block here and mark our normal, and then make sure light comes straight through to the normal point. Shine a ray of light at an angle onto a glass block, which has its lower face painted white or is frosted. Draw the outline A, B, C, D of the block on the sheet of paper underneath it. So first we have our sheet of paper, and we take our glass block and position it at the center of the sheet of paper. We trace out the edges of our glass block and label it A, B, C, D. Then we construct our normal using a protractor. Then we position our single slit and our lamp so that a straight ray comes to the normal point here. So we'll have our ray incident like that. Now this ray will be bended when it gets into the glass, and it will emerge at that point along CD, and it will continue in its path outside the glass block in the air. So what we need is to mark two positions along the incident ray and two positions along the emerging ray. Then we remove our glass block and we draw the lines, the line of the incident wave up to AD, the line of the emerging wave up to CD. Then at these points, we join these lines and we draw a normal here. Now we can measure the angle of incidence, the angle of refraction, and the angle of incidence when it comes at the point where the ray emerges, and the angle of refraction of the emerging ray. And here we'll find out that the angle of incidence is greater than the angle of refraction here when we are moving from air, which is an optically less dense medium, to glass, which is an optically less dense medium. And when we are moving from glass to air, the angle of incidence there is less than the angle of refraction. So light is bended towards the normal when we are moving from a less dense medium, air, to a denser medium. And light is bended away or refracted away from the normal when we are moving from an optically denser medium to a less denser medium. Thank you.